Meet the guide for our whole journey, a photon. A photon is the smallest packet of electromagnetic radiation we call light. Our glowing dot is only a teaching symbol. A real photon is not a tiny shining marble. Light can be described with both wave ideas and photon ideas. The wave picture helps explain patterns and travel. The photon picture helps us follow one packet of energy. Today, that packet will be our guide. We begin where sunlight begins, at the sun. One photon leaves along a smooth, planned curve. Its trail will become a measuring line. Our question is simple. How far can light travel in 1 year? Before that journey, we need to understand speed. Speed compares a distance with the time used, but ordinary speed also needs a viewpoint. We must ask, moving relative to what? Imagine walking forward inside a moving train. You move slowly relative to the train. You move faster relative to the ground outside. Both answers can be correct because the viewpoints differ. Spacecraft speeds need the same care. Voyager 2 moves about 15.4 kilometers each second relative to the Sun. Relative to something else, its number would differ. The reference point belongs with the speed. Now place our photon in a vacuum. A vacuum is space with almost no matter in the way. It is the clean comparison for light speed. Nothing in the lane pushes the photon forward. In vacuum, light travels exactly 299,792,458 meters each second. That is about 300,000 kilometers every second. Scientists use the letter C for this speed. The number is exact in meters per second. Here light does something surprising. Two steadily moving observers still measure the same vacuum light speed. Light does not simply borrow extra speed from its source. It keeps the same vacuum rule. Turn the source around and test again. Move one observer toward the beam. Move another observer away from it. Each still measures C for light in vacuum. Vacuum is not the only place light travels. Light also moves through air, water, and glass. In those materials, a light pulse progresses more slowly. The vacuum lane reaches the finish first. The material is full of charged particles that respond to the light. Their interaction changes how the wave moves through the material. We show that as a smooth delay. We do not show crashes or waiting rooms. After the pulse leaves the material, it enters vacuum again. The vacuum rule applies again. The path never needs a sharp corner. Our guide simply continues along its planned trail. Now our guide is ready to measure. Start a clock for exactly 1 second. In vacuum, light covers almost 300,000 kilometers. That huge distance is 1 light second. Let the same motion continue for 1 minute. Light then covers about 11.16 million miles. Continue for 1 hour. The distance becomes about 671 million miles. Hours fill a day, and days fill a year. The photon never teleports between those marks. Only the camera scale changes. The growing trail remains one continuous distance. After 1 year, the distance is about 9.46 trillion kilometers. It is also about 5.8 trillion miles. That distance has a short name, 1 light year. A light year measures distance, not time. The word year tells us how the ruler was made. Light supplied the known speed. 1 year supplied the known time. The trail between the endpoints supplied the distance. We can use smaller versions of that ruler nearby. The Moon is about 1.3 light seconds from Earth. Its arriving light is already about 1.3 seconds old. Even our nearest sky view has a delay. Sunlight takes about 8.3 minutes to reach Earth. That gap is 1 astronomical unit. It is roughly 149.6 million kilometers. We see the Sun from 8 minutes ago. A message from Earth to Mars takes about 4 to 24 minutes one way. The delay changes as both planets move. A reply must cross the gap again. Mars crews cannot be steered like instant remote control toys. Sunlight needs about 4 hours to reach Neptune. Seconds fit the moon, and minutes fit nearby planets. Hours fit the outer solar system. 1 light year is still enormously farther. Useful rulers change with the size of the map. Kilometers suit local trips. Astronomical units suit the solar system. Light years suit the gaps between stars. Astronomers also use parsecs on larger maps. 1 parsec equals about 3.26 light years. A megaparsec is 1 million parsecs. The universe stays the same, only the ruler changes. Now place Voyager 2 beside our Photon. Voyager is extraordinarily fast for a human-made machine. Its 15.4 kilometers per second is measured relative to the Sun. The shared reference makes this race fair. The Photon crosses 1 light year in 1 year. At its current speed, Voyager would need about 19,390 years. 1 calendar turns once. The other becomes a mountain of calendars. Voyager is not failing. The comparison reveals how enormous the course is. A light year makes a brilliant spacecraft look almost still. Interstellar distance changes what far means. The nearest star beyond the Sun is Proxima Centauri. It is about 4.25 light years away. Our Photon needs about 4.25 years to cross that distance. The unit now describes a real stellar gap. A message sent today would arrive about 4.25 years later. An immediate reply would need another 4.25 years. We would wait about 8.5 years altogether. That is a conversation across 1 nearby star system. Proxima's light also carries an old picture. The view arriving tonight left about 4.25 years ago. Distance tells us how long that light travelled. Place in space becomes a view from the past. Pull back until the Milky Way fits on screen. Its stellar disk spans more than 100,000 light years. Even light needs over 100,000 years to cross it. Our giant ruler becomes 1 tiny tile. Pull back again to Andromeda, our nearest major galaxy. It is about 2.5 million light years away. Its arriving light began travelling roughly 2.5 million years ago. Tonight's view is an ancient message. The galaxy has a present we cannot see yet. We only receive the light arriving now. Farther distance usually means an older arriving picture. Telescopes gather many different paths together. The moon arrives from seconds ago. The sun arrives from minutes ago. Proxima arrives from years ago. Andromeda arrives from millions of years ago. Go deeper, and the history becomes astonishing. Hubble observed GNZ11 as it was 13.4 billion years ago. That was about 400 million years after the Big Bang. The number describes look-back time, not its present location. Now return to the Photon we met at the start. It was our symbol for 1 packet of light. Its speed rule built a ruler. Its travel time also dated every arriving view. So how long is a light year? The name uses 1 year, but the answer is distance. It is about 9.46 trillion kilometers. It is the distance light travels in vacuum during 1 year. That ruler compares nearby stars, whole galaxies, and ancient arriving light. The farther we look, the older the picture can be. The night sky is not one live screen. It is a history book delivered by photons.